Hello. In the last lecture, we have seen what is meant by estimability degree of a parameter. So moving forward, let us see what is actually mean estimability of a parameter. So suppose f is some family of distributions and gamma is some parameter of this particular distribution. So whatever density is there in f, that is being guided by the parameter gamma. So this gamma parameter is said to be estimable of degree r if there exists a sample of size r based on which we can estimate gamma. So estimability degree of gamma is r. It means that it requires at least a sample of size r in order to get estimated. Now suppose we are provided with a sample of size r, and based on this, now estimability degree of gamma is r. So if sample of size r is provided, we must be able to estimate gamma. So if this sample is provided, then we are going to have some estimate of gamma based on this particular sample. So for that, there has to be some function, say h star, which will act upon these values x1, x2, xr. So this sample will get acted upon by a function h star, and this function will be such that whenever we take expectation of this function over all such possible samples of size r, we should get value gamma. So gamma is said to be estimable if there exists a function h star which, when acts on a sample, this particular quantity h star of x1, x2, xr, on expectation it becomes equal to gamma. This expectation is taken over this particular distribution from the particular family. Now this h star which is acting upon on this particular sample is said to be kernel. So this function which acts upon the sample is said to be a kernel, and this kernel is such that h star of x1, x2, xr, this on expectation gives the value gamma. So now we are saying that gamma is estimable because there exists unbiased estimator of gamma. So gamma is estimable and its degree of estimability is r. So for this particular gamma, we require a sample of size at least r, and this h star will then act on this particular sample so that expected value of this particular expression will be equal to gamma. So if this happens, then we say that gamma is estimable with degree r. Now suppose for the simplicity, let us take r is equal to 3 and gamma is the concerned parameter as usual. Now suppose we are provided with a sample, say 2, then 3.1 and then say 5. So this is the sample provided based on which we want to have some estimate about gamma. Now suppose there is some other person who has been provided a sample like this 3.1 to 5. So inference based on this particular sample and inference based on this particular sample, inference regarding gamma, this should not differ, because basically even if the order is different, these two are basically the same samples. So whenever samples of these particular types are provided, it doesn't matter the order in which the observations are being recorded, that order should not matter. So this sample should be treated equivalently like this particular sample. But whenever we are setting h star, we are not putting any condition on h star that it has to be symmetric in its argument or like that. So h star of these particular values and h star for these particular values may be different depending on whether h star is symmetric or not. So it might lead us to some different conclusion, like this particular sample will have some other estimate of gamma and this sample will have other estimate of gamma, which is obviously not favorable. So what we need is whatever be the order of observations in the sample, as long as composition of the sample is same. If you look at these two samples, composition of both the samples is same, only the order in which observations are being observed is different. So what we are expecting is this h star or whatever kernel we are applying, that has to be symmetric in its argument. So as long as its argument are 2, 3.1 and 5, it should give same value as the output, no matter what the order of these observations, order of these arguments is. But h star may or may not have that symmetricity condition. Therefore, we are having some other kernel function, say h, and these will be again defined on say these three values x1, x2, x3. but we are making sure that whatever kernel this H is, it has to be symmetric. So in order to make this H symmetric, we are considering all possible permutations of these 2, 3.1 and 5. Whatever permutations of these three values will be there, all those permutations will be considered, and therefore this H will be made symmetric. So this will be nothing but a star of x1, x2, x3, and these x1, x2, x3, or simply if we write like this x1, x2, x3, then we are fixing some order. So instead we will write alpha 1, alpha 2, alpha 3. Alpha 1 may be 1, 2 or 3. Similarly alpha 2 and alpha 3, they may be 1, 2 or 3. So for all these permutations, H star value will be calculated, and then it will be average will be taken of all those H star values. So this A is nothing but set of all the permutations of these numbers 1, 2 and 3. In this case, A will have 3 factorial, that is 6 elements in it. Therefore, in general, if we are having 3 elements, then we can write it as 1 upon 3 factorial summation of H star. So for all these permutations, H star will be calculated and average value of those H star will be taken. Since there are 3 factorial such permutations, therefore H of these will be equated to 1 upon 3 factorial and addition of all such H star values over all the permutations. So in general, if we are having a parameter gamma which is having estimability degree as R, now suppose we are moving towards general setup, R is any arbitrary value, positive integer. So gamma is estimable with estimability degree R. In that case, H of x1, x2, xr, it will be defined as 1 upon R factorial summation H star of x alpha 1, x alpha 2, x alpha R, and this summation will be taken over A, and in this case A is set of all the permutations of the numbers 1, 2, 3 up to R. So permutation of all these numbers will be considered, and then S star value for all those permutations will be calculated. Then average of all those values will be taken, and that will be regarded as H functions. Now whenever we are putting H like this, then instead of say x1, x2 and so on, if we are calculating x2, x1 and then x3, x4 up to xr. So I have switched only first two values x1 and x2. Instead of x1 and x2, I have written x2, x1. So even if order is shifted, then also H of these particular arguments will remain the same, because whatever input is there, that input will be circulated, that input will be permutated, input will be permuted, input will be permuted R factorial times. So even if this input is there, then also there are going to be R factorial such different orders. Even if this input is there, again R factorial permutations will be there. So all permutations will be taken into consideration while calculating this particular value. So H of this will remain as it is like this, H of x2, x1, x3 up to xr. So in this way we have defined a new kernel H, and this kernel will not depend on the order of its argument. So as long as these arguments are constant, as long as these arguments are fixed, H will give you same value even if order is changed. So in this way H is a symmetric kernel. So earlier S star was just a kernel, it may or may not be symmetric, but now we have defined a symmetric kernel by utilizing this particular S star. So now this H will be a symmetric kernel. So as we have seen that even if S star is not symmetric kernel, then also we can make a symmetric kernel by utilizing this S star. So henceforward, whenever we are saying a kernel, it will be understood that it is symmetric. If it is not symmetric, we can make it symmetric by certain calculations. So now we can say that gamma is estimable of degree R whenever there exists a symmetric kernel H such that expected value of H of x1, x2, xr is equal to gamma. Okay. So now based on this particular H function, we will see how to construct a U statistics. So for that, now consider the usual setup as a family of distributions. Gamma is the concerned parameter of the density of this density of some distribution from this particular family of distributions, and suppose it is estimable of degree R. then we are saying that there exists a symmetric kernel H such that H of x1, x2, x r, this on expectation will give you the value gamma. Now this gamma is estimable of degree r, and therefore this H demands r arguments, r inputs as its argument. But every time we may not have a sample of size r. Sometimes say we can have sample like this x1, x2, xr, xr plus 1 up to xn. So even if this gamma is estimable of degree r, we may or may not have a sample of exact size r. If we are having a sample of size less than r, then definitely we are not in a position to estimate gamma based on that particular sample, because this gamma is estimable of degree r. It means that a sample of size less than r cannot be used to estimate gamma. So the condition is clear, at least sample size should be r. If it is greater than r, if it is equal to r, then we can estimate gamma. So obviously if it is greater than r, then also we must be able to estimate gamma. In fact, it should increase precision of our estimation. So now suppose instead of r, we are provided with a sample of size n, where this n is greater than or it may be equal to r. If n is less than r, then we cannot estimate gamma. Now the sample is provided and that is having size n, but where this particular H takes only r values as the input. So this situation has to be tackled because sample is containing n values, but H requires only r values as the input. So even if we are having sample of size n, this particular H, this requires a sample arguments are in number. So for this, what we do, this x1, x2, xn, this is our sample. We select any r units, any r observations from this sample, and those will be provided as input to this particular sample. So input to this particular kernel. So this H will calculate its value, H of x1, x2, xr, output will be considered. Now again we will select some other r different values. Those r values, again H will be calculated, output will be stored. So this will be continued till now. If we are doing in this way, then out of these x1, x2, xn, we are selecting r units to give input to H, and this can be done in n, c, r number of ways. So out of these n samples, we will select a subsample of size r, and that only will be provided as input to this particular H, and all the values, output values, will be considered. So there will be n, c, r such combinations, and for every such combination of size r out of n observations, H value will be calculated, and then these all values will be taken into consideration and their average value will be considered, and that average value will be named as a U statistics. So now U statistics will be nothing but it will be average of all these H values calculated for different R combinations out of these n units. So x, say beta 1, x beta 2 up to x beta r, and this beta 1, beta 2, beta r, this particular say beta vector, this will belong to say B, where this B is collection of all possible combinations of r units taken out of n units. So if we are having n units, and if we want to choose r units out of those n, then how many combinations will be there? All those combinations will be listed in this particular B set, and from that B set, B bar is a particular value. So for that particular B bar vector, these x beta 1, x beta 2, x beta r, these units will be considered, H value will be calculated, and since there are n, c, r such values, while averaging we have to divide it by n, c, r. So U statistics will be 1 upon n, c, r summation of H of x beta 1, x beta 2 up to x beta r, and this summation will be taken over all such combinations. How many combinations of r units out of n units are getting formed? Summation will be taken over all such combinations. Okay. So that U statistics will be defined as 1 upon NCR summation of these particular thing. Now again you have to note that this H is a symmetric kernel. So while calculating this H, whatever operations we have done previously, all those operations will be performed. X beta 1, suppose this x1 up to xr, these values are chosen, then h, while calculating h value for these many arguments, h star of x1 x2 xr, then again permutation of these values will be taken, for that h star will be calculated, and so on, and then average of all those values will be taken, and that will pop out as h of x1 x2 up to xr. Okay, so using these particular operations, U statistics can be determined for the given sample. And as obvious, this U statistics will be unbiased estimator of gamma, because if we take expectation of this U statistics, it will be same as expectation of this particular expression. Since this is constant, expectation will go inside. Expected value of this particular thing will be again gamma. So gamma will come out, and this summation will be taken over NCR values. That NCR and this NCR will get cancelled, and its expectation will be nothing but gamma. So that this U statistics will be unbiased estimate of gamma. Okay. So based on H star, based on a kernel for the gamma function, for the gamma parameter, we have defined a symmetric kernel. Out from that symmetric kernel, we have defined a U statistic as unbiased estimator of gamma. Now there are some restrictions, there are some limitations. H star, it may or may not be symmetric, that was its drawback. H, even if it is symmetric, it takes only R values as the input, that was its drawback. So even if we are having sample of size n, H may not be in position to take n values at a time as the input. So H requires only R values as the input. So in order to remove this drawback or limitation, we constructed U statistic which systematically gives R values as the input to various H functions, and then for all these output values, their average value will be taken, and that will be named as a U statistics. Okay. Now suppose F is the family of distribution and gamma is the mean parameter. So suppose the underlying parameter is denoting mean of the population. So as obvious, a sample of size 1 is enough to estimate gamma, and therefore gamma is having estimability degree as 1. And as we know that expected value of x1 will be gamma, population mean itself, and therefore it simply implies that this function x1 is nothing but say a star of x1, where a star of x1 is such that it is an identity function. So x1 as it is, when it is taken, when expectation is taken over it, it gives value gamma. It means that it is identity function. A star of x1 is equal to x1, that function we have used. So in this case, h star, the kernel is nothing but identity function. And since there is only one argument, there is no question of symmetricity. So this h star can itself be treated as h. Therefore now we are having h of x as equal to x. This will be the kernel which we can consider to be symmetric, because since there is only one argument, actually there is no question of symmetricity. So h of x is equal to x, this will be the kernel for this particular gamma. So suppose now we are having a sample of size say n. We are having a sample of size n. Based on this, we want to estimate gamma. So as per the definition of U statistics, we have to consider all NCR combinations. In this case, NC1 combinations. So, and we have to take average of H values taken over those combinations. So we have to divide by 1 upon NC1. And the quantity that we have to consider is NC1. It is nothing but n. So there will be n such different values, and for out of these n values, we are selecting only one values. So that can be done in n ways. So expected value of x1 will be equal to gamma, expected value x2 will be equal to gamma, similarly expected value of xn will be equal to gamma. So now this summation will be taken over h of x r value, say x r, where this r or say xk, this r have different interpretation as it has been used for degree of estimability. So let us consider here xk, and where this k comes from b, where b is list of all such combinations of these particular n values taken one value at a time. So this simply implies 1 upon nc1. H of xk is same as xk itself, so it will be xk, and there are such n combinations in this particular. So k will belong to this particular set 1, 2 up to n. So in short, we are adding all sample observations and we are dividing it by nc1. nc1 is simply n. So this turns out to be 1 upon n summation xk, k running from 1 to n, and this is nothing but sample mean. So U statistics in this particular case is nothing but a sample mean. So as we know, sample mean is unbiased estimator of population mean gamma. So it turns out that U statistic sample mean for in this particular case is nothing but U statistic for this parameter gamma. Okay. Now again, suppose F has the family of distribution, and now suppose the parameter under consideration of this particular density from this family is say sigma square. So it denotes variance of the family of that particular family of distribution, and this sigma square is to be estimated based on a sample. Now as we know, variance cannot be estimated based on a single value. If we want to get some idea about the variability in the population, we should have at least two observations in the sample, and therefore this sigma square is estimable with degree 2. At least two observations are needed in order to estimate sigma square. So suppose x1 and x2, these are the two observations given. So this is the sample based on which we want to estimate sigma square. Now suppose a star as a function, say x1 square minus x1 x2. So I have defined a kernel as a star of x1 x2 is equal to x1 square minus x1 into x2. Firstly, let us verify whether this a star can be considered as a kernel for sigma square. If we consider expected value of a star, then it turns out to be expected value of this particular expression, which is nothing but expected value of x1 square minus expected value of x1 into expected value of x2. Since sample is random sample, observations will be independent, expectation can be split. Now expected value of x1 square will be, suppose if this family is having mean value as mu, then expected value of x1 square will be mu square plus sigma square minus expected value of x1, again it will be mu, this will be mu, so it will be mu square, and this will be sigma square. So that this particular kernel a star of x1 x2 is equal to x1 square minus x1 x2, this turns out to be unbiased estimator for sigma square. In short, this a star of x1 x2, this can act as a kernel for this sigma square parameter. But as we can see that a star of x1 x2, it will be different than a star of x2 x1. Only in the case when x1 and x2 are same, in that case only these will be same. A star of x1 x2 will be equal to a star x2 x1. In general, a star of x1 x2 may be different than a star of x2 x1, because this is nothing but x1 square minus x1 x2, whereas this is nothing but x2 square minus x2 x1. So even if these two terms are same, these terms are different, and therefore these two function values will be different. So a star is not symmetric in its argument. Therefore we will form another function h, which will be a symmetric kernel, and this can be formed for this particular sample, say x1 x2, as a star of x1 x2 and a star of x2 x1. Average of these two values will be taken. Since there are two arguments, therefore there are two factorial possible permutations of these values. That is, there are two permutations. Either we can take that in the order x1 x2, or we can take that in the order x2 x1. So these are the two a star values for these two permutations, and we are dividing by 2. So it will be 1 upon 2. A star of x1 x2 will be x1 square minus x1 x2. Again, a star of x2 x1 will be x2 square minus x1 x2. On simplification, this is nothing but x1 minus x2 bracket square. So this is our symmetric kernel, a star of x1, h of x1 x2. So whenever two values are given, we will simply take difference between those two values, we will square it, and we will divide by 2. This will be the h value for this particular sample. So even if order is different, order of this x1 x2 is different, we are only focusing on the difference between these two values. So this order will not matter. So now this is a symmetric kernel. Based on this symmetric kernel, we will form a U statistics. So suppose there are n sample values provided. Based on those sample values, we want to estimate sigma square. So for that, out of these n values, we can select only two values in nc2 number of ways, and For all such combinations, we have to take say x alpha 1 and x alpha 2, where this alpha will be taken from say B. B is set of all such combinations, all such NC2 combinations. So B will be set whose cardinality will be NC2. In set B, there will be NC2 number of combinations listed down. So this is just a particular one combination out of those NC2 combinations. So for all such combinations, H value will be determined and it will be averaged, and this average value will be U statistic. And if you perform simple algebra over here, this turns out to be sample mean square S square, which is unbiased estimator for sigma square. So whatever theory so far we have developed, all the statistics, most of the statistics are nothing but the U statistics. The motivation behind defining that particular estimate in a specific way comes from this particular S star, H and U phenomena. So this is all about U statistics. In the next lecture, so we'll see how this U statistics is used in estimation or survival analysis. Okay, thank you.